Now we're going to look at a new topic called direct variation. Varying directly is exactly what it sounds like. We are going to vary, which means change, but directly, so when one thing changes, everything else changes at the same rate. So some quantities have this relationship, and it's represented by a ratio of the corresponding value that's going to be constant. So this constant here we're going to call K, and it's going to be our constant of variation. Now when we're talking about a function, we always have an input and an output value. Our input value is X and our output value is Y. So our input and our output value are going to vary directly at a constant rate. So what is K? So K is the constant of variation. It is the amount that we're going to be changing by, but it's always going to be the same. That's what constant means. So when we have y equals kx, that means if I input values for x, it's going to change by the amount of k, and that's going to give me my y value. Now I can rewrite this and solve for k, and I get y over x. So every single time I find y over x, I need to have the same value of k. That's why it's called a constant. So here I'm given a table of values. I want to figure out, does this table of values represent direct variation? So is y and x varying directly? Are they changing at the same constant rate? Well, using that y equals kx whenever we vary directly, I can figure out if all of these three values will have the same k. And if they do, then we're changing at a constant rate, so yes, we are varying directly. So what we're going to do is we're going to write the ratio of y over x to see if it's constant. So for this first row here, y over x gives me 2 over 1, which is 2. The second row here I get 6 over 3, which also reduces to 2. And this third row I get 8 over 4, which also reduces to 2. So y over x is 2 for all of these, which means I can represent this table of values as the direct variation function y equals 2x. So this function here will represent this table of values. So remember, if this is a coordinate pair and this is a coordinate pair and this is a coordinate pair, if I were to plot these 3 points on the coordinate plane, this would be the line that would go through all 3 of those points. Alright, so now let's see if this table of values represents direct variation. So again, we're going to check y over x. So we get 4 over 1, well that's equal to 4. We get 8 over 2, well that's equal to 4 also. And then we get 11 over 3, which is not equal to 4. Okay, so this set of values here is causing me not to vary directly. So I am not able to represent this as direct variation. So this is not a direct variation. I am not able to represent this data in the form y equals kx. There does not exist a line in this form that will represent this data. So now we are given functions already written and we want to figure out, do they represent direct variation? So remember, all that means is, can I write it as y equals kx? If I'm able to write it y equals kx, then it is direct variation. So looking at this first problem here, I have 3y equals 7x. Well, let's solve for y. Solving for y, I divide by 3. So I get y equals 7 over 3x. So is it written in this form? Well, yes it is. And as a matter of fact, k is equal to 7/3. So my constant of variation is 7/3. Now let's look at this guy right here. Can I rewrite it as y equals kx? Well, first I want to isolate y. So isolating y, I'm going to have to divide everything by 7. So that's going to give me y equals 2x plus 1. Now, is that written like this? Well, no, it's not, because I have this plus 1 here. So this is not direct variation, and y is not varying directly with x, so I cannot represent it as direct variation. For this problem, we want to suppose that y varies directly with x, which means at the very beginning of the problem, we already know that this relationship, y equals kx, holds true for these values of x and y. So I'm given that y equals 9 whenever x is negative 15. So what we can do is go ahead and plug those values in. And since we know x and y, we can solve for our constant of variation. Now, since this value is constant over all pairs of x and y in this variation, I can use this same constant of variation to find any other missing coordinates from other coordinate pairs. So here, I'm given that x is 21, and we want to figure out what is y whenever x is 21. Well, that means we go back to this equation here. We know that x is 21 and k is negative 3/5, which means we can now solve for y. So y is going to be, remember, whenever we're multiplying a fraction times a whole number, you multiply numerator, numerator, denominator, denominator. So this is going to be negative 63 over 5. So whenever x is 21, y is negative 63 over 5. So this coordinate here, as well as the coordinate we started with, all lie on the same line of y equals negative 3/5 x. So these two coordinates here lie on this line since our constant of variation is negative 3/5. So let's try to put direct variation in a real-world context to really understand what it's telling me. So let's say you're a salesperson and your commission varies directly with your sales, which means that y equals kx is a true relationship between your commission and your sales. So let's say that for $1,000 in sales, the commission you get is $85. And then we want to figure out how much are you going to make off of $2,300 in sales. Well, first we have to figure out what is representing x and what is representing y. Now, x is usually our input values. What are we putting in? And then something happens to it. It is multiplied by k, and then we were getting out y. Well, I'm putting in $1,000 in sales, and I'm getting out $85 in commission, which means my y has to be 85 and my x is 1,000. So plugging that in, we can solve for k to figure out how much we're making on each dollar. So k is 0.085, which means I'm making 8.5% on every dollar. So I can go ahead and take k as well as my new sales amount and figure out how much my commission will be. So y equals my k, 0.085, times my sales, and multiplying those together, I get 195.5. Now what that means is on $2,300 in sales, I'm going to make $195.50 in commission. So I hope after looking at y equals kx over and over and over again, we can see that y equals kx is just a line. Now our slope is k, so our rate of change is k. Now your slope is constant on your line, just like your k, your constant of variation, is always constant. So whenever you're thinking of direct variation, I want you to make sure you're thinking of a line, but it's a line that goes through the origin. It always goes through the origin. So for this line, y equals 3/4 x, we are going to graph this. You can use a table of values if you need to, or you can just use your y-intercept as well as your slope. Now, since I have nothing added or subtracted, that means my y-intercept is 0, 0. My slope is 3, 4, so I'm going to go up 3 over 4. Up 3 over 4. I can also go down 3 to the left 4. And this would be the line that represents this direct variation. Okay, so whenever we're talking about x and y pairs that work for a direct variation, we're talking about coordinates that will lie on that line. Now you can make a table, but you should also remember that k is just acting as our slope. And this line will always have a y-intercept of 0, 0. I want you to determine whether y varies directly with x. Now, if it does, you can find the constant of variation, and you can write it as y equals kx. Now, I want you to suppose y varies directly with x, and then I want you to find k to be able to find what y is when x is 12.